Okay, we are back for part 2, and I am now at home working on this video, so you get to deal with the background noise of my life. Sorry about that. Hope it won't be too much of a distraction. Also, I have lost the Apple Pencil somewhere, and I'm going to be using my finger to draw on this with a new annotation software that I haven't really used much before, so we'll get through this together. It'll be great. Let's move on from where we were. We had finished talking about the tropopause. The next slide talks about, in some regions, the tropopause breaks and is difficult to locate. And here, unlike other places, scientists have observed tropospheric air mixing with stratospheric air and vice versa. And these breaks mark the position of jet streams. Those are high winds that meander in a narrow channel like an old river. But quite often they are extremely fast, unlike an old river, around 115 miles per hour. And if you'll notice, this is a map here from last week, late on Tuesday. If you recall, on Wednesday we had no school because it was extremely cold. So here we are, right here, just above where the jet stream dips down into the United States. And the jet stream typically marks a boundary. More often than not, the cold air will get brought down along with it from the north, and the southern warmer air can't get past it. It acts as a boundary for those air masses. So that's why it stayed so cold. The jet stream was down below us, and then when it warmed up, that was the jet stream moving back up, and the southern air then could get up to our area. So here, there we go. Okay, in the stratosphere, the air temperature begins to increase with height. That sets up a temperature inversion. Down here we have this isothermal zone, and then past that we end up with a temperature inversion where temperature increases with height. Because it gets warmer as you go up in altitude, the vertical currents of the troposphere typically don't spread into the stratosphere, and that also tends to reduce the amount of vertical motion in the stratosphere itself. So it's called a stratified layer, and that is simply because the air doesn't mix. It stays more or less in the same area that it ends up in. So we talk about the air temperature increasing with height, but I'd like you to notice up here at the top of the stratosphere, we are still at a nice toasty 0 degrees Celsius, 32 Fahrenheit. At the base of it, we are at negative 51 degrees Fahrenheit or less. The reason for the inversion in the stratosphere is due to ozone. Ozone plays a major part in heating the air at this altitude. No, honey, we're not almost home. Remember that ozone is important because it absorbs ultraviolet energy, and some of that will warm the stratosphere from below. If the ozone weren't present, the air would probably become colder with height, as it does in the troposphere. Back over in the notes on number 13, it says, what does temperature do with height in the stratosphere, and what causes it? Well, temperature increases with height, and that is because ozone heats up the air above it, but not below it. Also notice that the level of maximum ozone concentration is pretty far down in the stratosphere. A lot of people think about it being up in the stratosphere toward the top, but it's not. It's down it's in the bottom third. That's observed near 25 kilometers, but the air temperature reaches a maximum near 50 kilometers. The reason for this is the air at 50 kilometers is less dense than lower down, and so all that energy is still the same amount of energy that's hitting that part of the atmosphere, but there are fewer air particles there to absorb it, so they absorb more individually. So it's raising the temperature of fewer molecules to a much greater degree. So that's why that's another reason why the top of the stratosphere is warmer than the ozone maximum. Moreover, much of the solar energy responsible for the heating is absorbed in the upper part of the stratosphere and doesn't reach down to the level of ozone maximum, and due to the low air density, the downward transfer of energy is very slow. Okay, moving on. Above the stratosphere is the mesosphere. That's the answer to number 14, the mesosphere. or middle sphere. Meso is for middle. And the boundary that separates them is called the stratopause. That occurs right about 31 miles in altitude. The air at this level is extremely thin, and the atmospheric pressure is quite low. It averages about 1 millibar, which means that only 1/1000th of all of the atmosphere's molecules are above that level. So 99.9% of the mass of the atmosphere is located below the stratopause. So if you think about that, 99.9% of all the molecules in our entire atmosphere for the entire Earth are below that 30-mile mark. All of it is in the stratosphere and the troposphere except that 0.1%. So these upper layers that are up here, I'm pointing at them and you can't see me doing that. Sorry. These upper levels up here only contain 0.1% of the atmosphere, and yet they are actually the thicker the thicker layers. It's kind of interesting. The percentage of nitrogen and oxygen in the mesosphere is about the same as at sea level, but given the air's low density in the mesosphere, we would not survive breathing this air for very long. We would suffocate in a matter of minutes, because each breath of air would contain far fewer oxygen molecules than it would near Earth's surface. Other dire effects could be experienced in the mesosphere, such as exposure to UV rays, causing severe burns on exposed parts of the body. Not that you'd have many exposed parts of the body if you were floating around in the mesosphere, but, that's what would happen. Also, given the low air pressure, the blood in one's veins would begin to boil at normal body temperature. If you think about the way that temperature and pressure interact, we are going to talk later about rocks, magma underground here on Earth, and pressure and temperature are going to play a big role in whether they melt or not. It's the same idea. Because the air pressure is so low, the blood in your veins would require a much, much lower temperature to reach its boiling point. So at normal body temperature, it would be above that, and that would be bad. So this slide here is basically what you need to answer number 15. Number 16 asks what happens to air temperature as you increase in altitude in the mesosphere. That is right here. The air temperature in the mesosphere decreases with height, due in part to the fact that there is little ozone in the air to absorb solar radiation. And the molecules, especially those near the top, are able to lose more energy than they absorb, which results in an energy deficit, so we have cooling. The air in the mesosphere becomes colder with height up to an elevation near 53 miles, and at that altitude, the temperature is a nice brisk negative 130 degrees Fahrenheit. That makes the mesosphere the coldest layer by far of the atmosphere. So that takes care of number 16.